Welcome to Chapter 2. Data Models. In Chapter 1, we explored the fundamentals of databases. Now, we focus on how to design them properly. This chapter is divided into 4 parts. In Part 1, we focus on the database development process and the different types of data models used along the way. We will see how a database moves from an initial idea to a working system, and how data is represented at each stage. Let me start with what you should be able to do by the end of this part of Chapter 2. There are 2 learning outcomes. First, you will be able to apply the database development process and understand the different levels of database design, from the abstract, conceptual level down to the physical level. Second, you will be able to distinguish between the different types of data models and apply them appropriately in database design. As with every chapter, we have 2 references. The first is our own faculty's lecture material on databases, which follows this chapter directly. The second is the Cornell textbook. Here we draw on several chapters, including chapters 2, 3, 4, and 10, since data modeling connects to many parts of the book. As always, use the lecture material as your main guide, and turn to the textbook whenever you want more detail or additional examples. Here is our roadmap for the chapter. We will begin with the database development process, then look at the types of data models. From there we move into the entity relationship model, and the relational data model. Finally, we will learn how to convert an ER diagram into a relational model, and close with relational algebra. In this first part, we focus on the first 2 topics, the development process and the types of data models. The rest will follow in the next parts. Let's start with the first major topic, the database development process. Before we design a single table, it helps to understand the full life a database goes through, from the first study of the problem to long-term maintenance. The database development process is described by the database lifecycle, or DBLC. This is the life cycle of a database within a larger information system. The DBLC consists of 6 phases. First, the database initial study, where we understand the problem. Second, database design, where we plan the structure. Third, implementation and loading, where we build it and bring in the data. Fourth, testing and evaluation, where we make sure it works. Fifth, operation, where the database goes live. And sixth, maintenance and evolution, where we keep it healthy and adapt it over time. One important point, the DBLC is iterative, not strictly sequential. We often loop back to earlier phases as we learn more. Keep that in mind as we walk through each phase. This diagram shows the 6 phases of the database lifecycle and how they flow into one another. Notice the feedback loops. The arrows don't just move forward. At almost any stage we may need to return to an earlier phase to refine our work. That circular, iterative nature is exactly what makes the DBLCA lifecycle rather than a checklist. Let's look at the first phase, the database initial study. The purpose here is to understand the situation before designing anything. There are 4 tasks. We analyze the company's situation, define the problems and constraints, define the objectives, and define the scope and boundaries of what we're building. 2 ideas are worth stressing. First, a good designer finds the real source of a problem rather than just treating its symptoms. And second, we always work within real-world constraints, time, budget, and people, so we must distinguish between what would be perfect and what is actually feasible. The second phase is database design, and this is where the levels of design come in. The design process moves through 3 levels, going from independent of the technology to fully dependent on it. We begin with conceptual design, which is independent of both hardware and DBMS. Then we select the DBMS software. Next comes logical design, which depends on the type of DBMS but not on the hardware. And finally physical design, which depends on both the DBMS and the hardware. As with the whole life cycle, design is iterative, with continuous feedback rather than a single straight path. We will return to each of these levels in more detail shortly. The third phase is implementation and loading. The output of the design phase is essentially a set of instructions for building the database, defining tables, attributes, domains, views, indexes, and security constraints. There are three main activities. First, we install the DBMS. Second, we create the database itself, where the storage structure follows a hierarchy: storage group, then table space, then table, and third, we load or convert the data, migrating it from the old system. Sometimes writing conversion programs when the old and new formats don't match. Database security is also a key part of implementation. Data must be protected from unauthorized access, loss, destruction, and misuse. There are three main security goals: integrity, confidentiality, and availability. A threat is any situation that could harm, misuse, or cause loss of data, and it can come from either inside or outside the organization. So, how do we defend against these threats? We use several layers of security. First, physical security controls access to sensitive areas. Second, user authentication and access rights ensure that only authorized users can log in and perform permitted operations. Finally, audit trails record who accessed what, helping us detect and trace security violations. Together, these measures help protect the database from unauthorized access and misuse. To complete database security, we also need data encryption, which protects data from unauthorized use. Encryption can use either a single shared key or a public and private key pair. Security also depends on policies, trained staff, backup and recovery, as well as tools such as antivirus software and firewalls. Together, these technical and organizational measures provide stronger protection for the database. The fourth phase is testing and evaluation. Here, the database administrator tests and fine-tunes the database to ensure it works as expected, often alongside application development. Testing focuses on data integrity and security, while evaluation looks at the database and applications as a whole, including integration, user training, and documentation. Backup is also important, including full backups, differential backups, and transaction log backups. The fourth phase is also about understanding database failures and recovery. Failures can come from software, hardware, programming errors, or external events such as fire or flooding. When a failure occurs, recovery starts from the latest consistent backup, then uses the transaction log to restore committed changes or undo uncommitted transactions. The key lesson is simple: without a backup, recovery may be impossible. The fifth phase is operation. Once the database passes evaluation, it goes live and becomes part of a complete information system, bringing together the database, users, management, and applications. But operation is also the beginning of continuous evolution. Real-world use may reveal new problems, such as performance bottlenecks. These can be addressed through solutions like load balancing or increasing DBMS cache. The key idea is, once a database starts working, it also starts evolving. The sixth and final phase is maintenance and evolution, an ongoing responsibility of the database administrator. Maintenance includes preventive maintenance, such as regular backups, corrective maintenance, such as recovery after failures, and adaptive maintenance, such as improving performance or adding new data requirements. The DBA also manages access rights, monitors security, and conducts periodic audits. When the database can no longer meet new requirements, the DBLC starts again, making it a continuous cycle. Now that we've seen the life cycle, let's look at two broad approaches to database design. The first is the top-down approach. It starts at the conceptual level and gradually moves into more detail, focusing on the key objects the system needs to store. There are three main steps: identify the entities, identify their attributes, and then identify the relationships among them. When applied correctly, this approach naturally leads to a well-normalized database. The second approach is the bottom-up approach. It starts with actual data and progressively groups and normalizes it to reduce redundancy and improve consistency. There are three main steps: collect data elements, group them into entities, and identify their relationships. The two approaches complement each other, bottom-up works well for small databases, while top-down is better for large, complex systems. A simple way to remember them: ER modeling is top-down, while normalization is bottom-up. This diagram brings together the levels of database design we've been discussing, moving from the conceptual level, which is independent of technology, down through the logical level, and finally to the physical level, which is tied to a specific DBMS and hardware. Keep this picture in mind as we now examine each level in turn. Let's start with conceptual design, the first and most abstract level. Here, we create a data model that represents real-world objects while remaining independent of specific hardware or software. A key principle is the minimal data rule: include everything needed, but nothing unnecessary, while allowing for future needs. Conceptual design has 4 steps: requirements analysis, ER modeling and normalization, model verification, and, when needed, distributed database design. We'll explore the first 2 in more detail next. The first step of conceptual design is data analysis and requirements, understanding the organization's actual data needs. We focus on 4 questions: what information is needed, who uses it, where does it come from, and what does it contain. This includes its attributes, relationships, volume, and frequency. To gather this information, we study user views, observe existing systems and reports, and work closely with the systems design team. The key is to understand the data and how the organization uses it. The second step is ER modeling and normalization. First, we establish common documentation standards, including symbols and diagram conventions. Then we identify the business rules, entities, relationships, attributes, primary and foreign keys, and normalize the entities. We create the initial ERD, verify it with users, and revise it based on their feedback. Remember, normalization may reveal new entities or attributes, so revising the ERD is a normal part of the design process. The next level is logical design. Its goal is to transform the conceptual model into a logical model that can be implemented in a relational DBMS. Before mapping, the conceptual model must be properly normalized. Logical design has 5 phases: create and validate the logical data model, define integrity constraints, merge the models, and review the final model with users. The key point is that user feedback remains important throughout the design process. The final level is physical design. Its goal is to define how data will actually be stored and accessed in the DBMS, with a focus on efficient storage, security, and performance. Physical design has 7 phases: analyze data volume and usage, create tables, choose file organization, define indexes and views, estimate storage requirements, and determine database security. This is the most technology-specific level, closest to the actual DBMS and hardware. Before we leave the design process, let's focus on business rules. A business rule is a clear and precise statement of an organization's policies, procedures, or principles. Business rules apply to any organization that manages data, and they should be documented and updated as requirements change. For example, a customer may generate many invoices, but each invoice belongs to only one customer. A training session may also require 10 to 30 employees. These rules define real-world constraints that we later represent in the database design. Where do business rules come from? The most reliable sources are managers, policymakers, and department heads, along with written documentation such as procedures, standards, and operations manuals. There's also a faster, more direct source: interviewing the end users themselves. But be careful, this can be less reliable, because different people perceive the same process differently. So the designer has an important job here, to reconcile those differences and verify the rules, so that what we end up with is accurate and appropriate for the organization. Business rules provide several important benefits. They standardize the organization's view of data and improve communication between users and designers. They also clarify data, business processes, relationships, and constraints, helping create a more accurate model. However, not every business rule can be enforced by the data model. For example, a student's credit limit per semester may need to be handled by the application. Understanding this boundary is an important part of good database design. That completes the development process. Now let's turn to our second major topic, the types of data models. This is the toolkit we use to describe data throughout that process. Let's begin with what a data model actually is. A data model is a set of symbols and rules for describing data, the relationships among data, its meaning, and its constraints. A good data model represents several things at once: the data structures, their characteristics, the relationships between them, the constraints, and how data can be transformed. There are many different data models, each reflecting a particular way of thinking about data, and databases can differ both in function and in the model they use. Why does this matter so much? Because a data model substantially reduces the risk of errors in design. And it acts as a communication bridge among three groups: the designer, the application programmer, and the end user. It gives everyone a shared language. This table shows the generations of data models, how they evolved over time. From the earliest file-based and hierarchical models, through the network and relational models, to the object-oriented and NoSQL models of today, each generation arose to overcome the limitations of the one before it. It's a helpful reminder that data modeling is a field that keeps evolving. Let's organize the main data models by their level of abstraction. At the conceptual level, high-level models describe data close to the real world, such as the model and object-oriented model. At the logical level, implementation models describe data in a form that can be built into a system. The relational model is the dominant approach, using tables, rows, and columns. The older network and hierarchical models were largely replaced because they offered less flexible querying and made applications more dependent on the data structure. Finally, at the lowest level, we have the physical model. It describes how data is actually stored, including file structures, indexes, and record layouts. Because it is closely tied to storage and the DBMS. The physical model depends on systems such as SQL Server, Oracle, or MySQL. So, we move from the conceptual model, close to the real world, down to the physical model, close to the hardware. Each level plays an important role in good database design. That brings us to the end of part 1 of chapter 2. We've covered a great deal: the full database lifecycle from initial study to maintenance, the 3 levels of design, the role of business rules, and the different types of data models. With this foundation in place, we're ready to move into the entity relationship model itself, where we'll start drawing the diagrams that turn these ideas into real database designs. See you in the next part.